So I will just start with the definition. I will recall things from yesterday as we go along and as we meet them. So we have yesterday talked about wrinkles themselves, just model wrinkles, standard wrinkles. And now using that, we can make a definition, what is a wrinkle submersion? So map F from an n-dimensional manifold to a q-dimensional manifold is a wrinkle submersion. If there exists disjoint embeddings phi j from, okay, let me just say open neighborhoods. No. Okay. Let me recall briefly. We had the standard wrinkle W. It was from some subset of Rn to some subset of Rq. And we had that there was this q-dimensional disk, and on the boundary of the two-dimensional disk is where it's singular. So on the boundary is mapped to something like this, and over the boundary we have the wrinkling happening. And so let me just say I take a small open neighborhood of this q-dimensional disk in Rn and restrict the wrinkle to that small open neighborhood. So I think of it as a germ on the small neighborhood of this disk where the interesting stuff happens. So and I will use this for following definition. So this is from these open subsets into V. So those should be embeddings such that we have the following diagram. So we have F from V to W, then, and let me write the dimensions here so we understand what's going on. Then we have this embedding here, one of those phi j epsilon. Then here we have the standard wrinkle going to RQ. Now we're in the same dimension, and then I want to have another embedding, or I think one could start with an immersion such that this diagram commits for every j. So there's finitely many, say j from 1 through n, such that over the images of each of these dimensions of these embeddings, it looks like a standard wrinkle. And outside, so you should think now of V as having the images of these embeddings here. Over those images, it looks like a standard wrinkle up to composition with some immersions or embeddings. And outside of the images, it should just be a submersion. So the only places where it's not a submersion is where it's a standard wrinkle. And submersion outside the union over all j of the images of these embeddings. Yeah. So it's a submersion except for standard wrinkles.
Could you elaborate why you take a immersion downstairs?
Actually, one doesn't have to. It's somehow convenient because somehow out of the proof, sometimes you just get an immersion and not an embedding right away. But I will explain later today, there is an operation that you can, once you have a wrinkle, you can chop the wrinkle into smaller ones. And then if you somehow have an immersion and you chop your wrinkle into smaller pieces, then you restrict to each of these smaller ones is going to be an embedding. Okay, so I could have equally well said embedding here. Nice. Okay. Now, with this, we can state an H principle. So I need to say one more thing. Once I have a wrinkled submersion, then we have a regularized differential. So if we just take the ordinary differential, that fails to be surjective over the singular set on the wrinkles. But as I explained in the end yesterday, you can take the differential of a standard wrinkle and you modify the differential in a canonical way to make it something which has full rank. So that we call it the regularized differential. We can do for every wrinkle, and of course outside it's anyway already surjective. So this is an epimorphism, so it's linear surjective. Now, and since maybe, let me just recall, I should have given that picture maybe yesterday. So this is a one-dimensional standard wrinkle, and the differential is just the derivative of this function whose graph this is, but the regularized differential will be the derivative here, but then over the wrinkle part, we replace the part where the derivative becomes negative by making it positive. That was the definition of the regularized differential. So I just explained it like this. Okay. So the map actually goes down like this. It has negative derivatives, but we define its regularized differential by just keeping the derivatives positive throughout. Yeah. Okay. Now I'm ready. See you. This Cieliebak, Mishachev, 27. That wrinkled submersions satisfy the full H principle. That means relative parametric H principle. So let me maybe just state the simplest case, which is not relative and not parametric. So what does it mean? We are given any map from V to W, which is not a wrinkled submersion, it's just any continuous map. Then we have over it, we have the tangent bundles. And this map, let me maybe call it F0. This is covered by an epimorphism, which has nothing to do with the derivative of F. Yeah, so this is the formal data. We just have a map between the manifolds, which is covered by a formal solution of our differential relation. Differential relation for submersion means the differential is surjective. Right? So I have a fiber-wise linear map, which is everywhere surjective again, the dimensional n and q. And of course, now I should say that n is greater than 2k. So, and then I can deform this map to a wrinkled submersion. So I find a homotopy of maps. I'll complete this item in a second, such that F1 is a wrinkled submersion. And this should be C0 small downstairs. And it's covered by a homotopy of epimorphisms such that F1 is the regularized differential of dF1. So not only can I approximate my arbitrary map by wrinkle submersion, but if I started with some formal data, I can do it in such a way that the regularized differential of this wrinkle submersion by which I approximate is the given formal data that I started with. So that's what the Edge principle should tell you. Now this would be zero parametric. If you want to do it with parametric version, then you can say the manifold V is equipped with a foliation and you do everything leafwise. That would be one thing. So you just add some F for foliations here in the picture. Yeah, that's clear. Yeah.
So the regularized differential is equal close to F0, the capital F0.
Yeah. Right. Okay. I think you can, the way it's grouped. Yeah. It will be zero. Yeah. We see the proof is really some holonomic approximations also. I think
I mean, somehow the regularized differential is only defined up to homotopy anyway, so you take ft constant if you want.
yes,
Down the left.
you could, right. Well, but but then, okay, I don't know, but I don't know that then I can construct the wrinkle submersion so its regularized differential is exactly something I prescribed. So that I actually don't know. I might have to wiggle it a bit later. Because I mean in the proof you have to do some interpolation, so you're staying close, but it's maybe yes, but I'm not sure that you can do it like to prescribe it exactly. Then I'm not sure. Okay. Let me maybe comment if it's in the parametric case. So what does it mean? So what is in the one-dimensional case, we still have the picture here. So in the one-dimensional case, a standard wrinkle is just a pair of critical points together with some connecting trajectory between them, right? Now, so that would suggest that if you do it, that you should only find this kind of singularity if you're talking about functions to R. But if you do it parametrically, there's one additional phenomenon happening, namely that wrinkles can disappear as you move in parameter space. So in the parametric version, wrinkles can appear or disappear through embryos of wrinkles. So there you can write the definition, which I'm not going to write, of an embryo of a wrinkle. And so the wrinkles can shrink and then they disappear through an embryo of a wrinkle. So this has the effect that in the parametric version, for example, for the case Q is equal to 1, so for functions f from V to R, now a wrinkled submersion has only most critical points. It's just which are organized. So this is wrinkled submersion, and only if it has only most, I mean, non-degenerate critical points organized in pairs of adjacent indices, like in this picture. But in families of such functions, we're going to also see these pairs of critical points move together and disappear. So we see something like that, that this can move together to become this and this. So we see this movie going this way or the other way. So the pairs can appear and disappear. So that the kinds of functions that we see in families will be what is called generalized Morse functions. Yeah. So Morse functions which have either Morse singularities or these birthday type singularities. Yes. Let me just finish right then.
Higher dimensions or families of Morse functions can have multiple critical points.
Yeah, but the no, it only happens in this way. So because when you move to, the thing is that if you do it in Primogic, then this is the parameter space. You have a wrinkle in parameter space like this. Now over the wrinkle, when you restrict to a fiber, you just see this pair of critical points. And when you move to the boundary, this pair of critical points moves together and disappears. And this happens in whichever direction you go to the boundary. It's always, you always see the same thing. You see a pair of critical points moving together. So the singularity doesn't get any worse than this, even in high dimensional families. Yeah. So that's the surprising thing about this, that somehow, yeah, you get one additional kind of singularity that they can move together. So you need to go to get generalized Morse functions, but it's not getting worse, and that independent with how many parameters you do it. Yeah.
How much control do I have over the wrinkles that appear? Like, can I make them very small in the domain, for example?
Yes, you can.
Is there like a best statement you can make along those lines?
Well, I don't know what the best statement would be, but I mean, certainly I could make a statement that the wrinkles can be arbitrarily small. So both in the manifold and also in parameter space. So there's a general procedure which I hope to mention in the end.
On the target.
Well, then also in the target. Yeah. Mm-hmm. Everywhere. Mm-hmm. Yeah. So I can make them small everywhere. So there's a procedure that you can take any wrinkle that you have and you can chop it into smaller ones. So I mean, you take what you get first, but then afterwards you can start then somehow make the wrinkles smaller.
There's also this Phillips submersion theorem where you don't have wrinkled submersions, but submersions, but in a both sides, I think, open. Is it like you just push the wrinkles out to be manifold to infinity?
Yes, although I don't know how I would derive it from.
Okay, I was wondering whether you could derive
one.
this.
Yeah, so I don't know. I don't know. So this I don't.
No, I mean, you can pick a core that avoids the wrinkles.
The wrinkles are for the top dimension itself.
Okay, maybe you can just.
I mean, we already proved Phillips would, because it's different.
Yeah, I mean, we already did it. Yes, so I think it's easier to do it from the way we did it already. Okay, so.
Sorry, can you just recall once again what was generalized Morse function?
Hmm?
What's the generalized Morse
So
function?
generalized Morse function is a Morse function which has only non-degenerate critical points or critical points as they appear in a one-parametric family. Which I think I wrote a model yesterday where the second derivative vanishes in one direction and the third derivative doesn't vanish in that direction. In terms of singularities that we discussed yesterday, this Tom Boardman singularities, I could also say that they only have sigma 1, 0. So this corresponds to non-degenerate critical points, and sigma 1, 1, 0. This corresponds precisely to these moments.
Maybe a comment, I guess, is that I mean the space of, let's say, maps that have generalized, like wrinkles or embryos is not the same in some sense as this, right? Like these are, as you're saying, they're like organized
Yes.
in a nice way. Like
Yes,
even
yes,
in
yes.
family, so.
Yes. So it's somehow, but generalized most function is more general than what we get here, because again, everything, they come organized in pairs. So the most singularities come organized in pairs, and then only in those pairs can they disappear. Yeah. So if you have an arbitrary generalized most function, there's no canonical pairing between the critical points. Yeah? So it's more special than that one, and we're going to use it in the third lecture today. So what we're actually going to see is what we're then call Igusa functions. So it's somewhere where they are organized in space. Yeah.
So for a wrinkle function, because of the organization in pairs on a closed manifold, could these only exist if the Euler characteristic is 0? Is that true?
That's very true.
Yes, that is true, because you need, as a formal data, you need a nowhere vanishing vector field, which is the potential gradient of your function, right? We're talking about submersions to R, right? So the formal data is like a submersion to R, a function without critical points. A function without critical points, you take its gradient, you have a vector field without critical points, then the order capacity is 0. Yes, that is true. Yeah. So in the third talk today, I will say the more general result, which applies to arbitrary manifolds and many units. Any more questions? Okay, now let me try for the rest of this talk to explain a little bit about the proof. And the proof is in several steps, but let's focus on the first two steps. And the first step is multi-valued polynomial approximation. So this relates back to what Dani explains us, but it's actually easier in a way. So Dani's construction was fundamentally two-dimensional. So what Dani explained to us, you have a mountain that you want to go up, and you're over the plain, and you want to go up that mountain, and to go up that mountain range, you do this twist backs. So you always go horizontally, but you use both dimensions to get something which is nicely embedded, and it's doing all these turns and working its way up. And then you can somehow interpolate along here where you have a lot of space to get a good polynomial approximation. Now, so this is fundamentally two-dimensional, the ordinary polynomial. Now suppose we only have one dimension at our disposal. So we only have one dimension, and we still want to go up a mountain, right? Now we cannot do this toy because it's just one dimension, right? But what we can do, maybe you had this as a kid. There's this toys you can have a slightly tilted bar with something lower in between, so you can run a little ball in there. At the end of this bar, the little ball drops to another one, onto another one. Then the ball runs down here, and it drops, and it runs down here, it runs down here, it runs down here. Any one of you played it? I think I love that. Anyway, yeah. So this was really a one-dimensional thing. You had this thing on one on top of the other, and there was just little holes, and the ball was dropping. So this is a way to just having one dimension at your disposal to work your way up, right? And that is what multi-valued polynomial approximation is, because this map, if you project this thing down onto the plane, or if you rather go the other way, then it's becoming multi-valued. So this is a multi-to-one map. So it's not an embedding anymore in this one-dimensional line. Right? It's something going back and forth. And also the other thing is that something funny happens here, because this looks like something a little bit singular. Yeah, so, and we'll have to, there's two ways of dealing with it, and we'll first do it with the multivariate tolerable estimation, and afterwards we're going to smoothen a bit more out. So, okay. Now, having given you this picture, let me make a formal definition of what is the multivalued or multifolded, I think I should say multifolded interval. Let me at least be precise at one point here, so I can give you a nice definition. So we pick numbers. We start with 0, A1, A2, A3, up to some AN. We pick another sequence of numbers, B1, B2, B3, which are bigger than these ones. Okay, so we're organizing them like this. So I'll draw the interval, and let's say the last one, Bn, is equal to 1. Okay. So here's 1, here's 0. So we have A0, and then we can go all the way to B1, and then we have A1 below here. We have B2, we have A2 below here. Now, over this, I need some colors for this. We're going to build another space as the union of intervals. So we'll have intervals of this type. This I will call maybe A1. It goes from A0 to B1. Then I have another one from A1 to B2. This is A2. And so on. Okay. Then we take shorter intervals, which go just here. This is, say, B1, B2, and so on. And then use yet another color to connect these intervals up. So we are identifying now, so these are all open intervals, and we are going to identify the endpoints here and the endpoints, some open intervals here and some open intervals there. So yeah, I take some small open interval at the end here, which I just identify. I define the quotient topology with this interval which is above it. And then I identify this one. And likewise, I identify some small open, this way, identify it here and then here. So that we are somehow going back and forth.
So small means that they don't intersect.
Sorry?
By small, you mean that these two intervals don't intersect each other.
Yeah. Those two intervals don't intersect each other. Yeah, just pick a small number, so they don't intersect. They don't overlap. And then what we'll find is that if I draw a picture of what this looks like afterwards as a space, it's going like this, then it's turning back up like this, and it's going like this. It's turning back up like this, and going like this. Yeah. So this is somehow the space when I glue these things, and I just draw it as one space. So let's call this I hat. And downstairs is our standard interval I. And we have obviously a projection, let's call it I. On this space also the standard interval. Right? So somebody will probably ask this question. So this I hat is non-Hausdorff, yeah? Because I do everything with open intervals, I'm gluing open intervals. So it's not something that we usually like doing in topology because it produces non-Hausdorff spaces. But we'll see that it's good enough for purposes. But you wanted to maybe add something else?
Yes, so in this construction, to me it seems important that also B1 is smaller than A2, for example.
No.
No?
Well, I mean, B1, wait, B1 is smaller than A2. It's probably not important. I think it's only important that, I mean, I can glue the end point of this one and this one. So for other ones, it doesn't matter.
Then it will be more than 2 pre-images. in some places.
It could be actually, yeah, it wouldn't matter. Okay. I think we're usually only needing this picture. We don't need to make it more complicated than it's interlinked like this. So that's good enough for everything that we want to do with it. But for the definition, I think you could know this also. So this would be a multi-folded interval. It depends, of course, on a lot of choices, like how many, like this number n, and also the precise choices of these numbers. Yeah, so it's not a unique one. Somehow we have some freedom in choosing it. Now once we have this for an interval, we can define a multi-folded cube. Yeah.
I think I'm now confused about the comment you made, because I think like when you're like using this multi thing to interpolate very, very slowly, you will need in fact a lot of overlap of these intervals, no?
Actually, they will, okay.
Right, you have a lot of space,
Actually, yes. Actually. Okay, actually, I think you're right. Actually, yes, I will need it in a way where it's where they overlap a lot, so that somehow we have the A intervals really rather like this, yeah, the same, and the C interval, and then we connect back, and so the way they do intersect a lot. You're right. Actually, in the construction, we are rather going to see where they overlap a lot, so that we have a lot of room in this direction to do the integration. Thank you. Yes. Okay, so multi-folded cube is n-dimensional cube. Projects onto the standard cube, and you can define it as the n-1 dimensional cube times the multi-folded interval in the last direction. But you want to identify something, I'm going to say, namely, if I draw a two-dimensional picture, then say in this direction, I want to take the folded interval. So this becomes something like this. And as I go to the boundary of this square, I want to undo the folding. So, which means that somehow, somewhere near the boundary, I don't want to have any folding. So I don't want to continue all the way to the boundary, but I want to cut it off near the boundary. So then the way you do it is that as you approach the boundary, you just collapse this multi-folded cube completely onto the standard cube. So as you're close to the boundary, you identify everything here which is sitting over the same point. You just collapse it, and then you just see a standard interval. Okay. So this is somehow the picture of a multi-folded cube, and then a multifold you can define is a map from an n-dimensional manifold to an n-dimensional manifold, which looks like this, that it's just having some multifolded cubes inside, and outside is just the identity. So the V head is just the V with a couple of multifolded cubes embedded in it. Yeah. So you take your manifold V, you embed a couple of cubes in there, and over each cube you take a multifolded cube. And because we cut off the multifolded cube to the standard cube near the boundary, then it fits outside. Yeah. So that's okay. Now we can talk about multi-sections in a fiber bundle. So a multi-section in a fiber bundle X over V. This is, so let me draw X over V. Then it is, we take some multifold over V. So we introduce some multifolded cubes in V, and then we have a map which is defined up here. Yeah. So rather than having a section from V to X, is we go to some multifolded covering of V, a multifold which is sitting over V, and we have a section which is living here. Okay. So that is such that this commits, yeah. So that's a multi-section. Yes.
Multifold is something is similar to a mapping from B to B with a lot of
Yes. Yes. Mm-hmm. And now we can say that multi-section of an RJ space. So what is that? So we have the RJ space now associated to this vibration. So a multi-section would be, again, we have a multifold and we have capital F that it is. And now this multi-section, we can say what it means to be holonomic. Let me just finish writing this, yeah. Holonomic if this is the object of a holonomic of a multi-section in the original bundle. And that makes perfectly sense. You can talk about jets here, yeah, because somehow we're just gluing some open intervals, but everything still looks like we can talk locally. You can take derivatives of these things in all directions. You take hair derivatives, you can take jets of these objects. Yeah. So
I think I missed something in the definition of the interval,
Mhm.
the multifold interval, because I cannot see why it is not also.
Okay. Yes, because when you take two intervals, say an interval AB and another interval, say, okay, let's take say A0, B1, and we have the interval A1, B1. And the first gluing that we're going to do is we're identifying point X here with a point, with the same point X prime. Well, okay, this is always difficult to say what is the, well, okay. X is identified with its image X prime, but it's really the same point. If it is in the open interval B1 minus delta B1.
The topology is the pre-image of.
And the topology is a quotient topology. So, well, you have a projection now from the disjoint union of these two intervals. I mean, I'm taking the disjoint union and then I'm doing this gluing, right? With the quotient topology, and the topology is a topology so that the quotient projection becomes continuous. Yeah.
Okay, thank you.
And that is non-Hausdorff. And it's non-Hausdorff because it is open here. Yeah. It's not essentially it's open here at the end point of B1. That wouldn't make a difference, but it's open here, and therefore it's non-Hausdorff. Yeah. Okay. Right, so we can talk about holonomic multi-sections. And now we can state a multi-valued holonomic approximation. At least I had 4 beautifully clean boards to start with. So every section F of the RJ bundle can be C0 approximated by a holonomic multisection. So the picture is the following. We are having the RJ bundle. We're given some section F, and then there exists some multifold. Okay. So that you find a holonomic section from here. So it's a holonomic multi-section, which is C0 close to F in the sense that if you take this section that F hat is C0 close to F composed with this projection. Yeah. Those live on the same space, and we can say that those are C0 close. So it's in that sense it's C0 approximates. Okay, and the proof I will do by pictures. So without loss of generality, D is just the cube itself. Okay. So we can localize it by chopping off as an exponent to statement over the cube. So we have a section now over the cube. So what we'll do is this section we can restrict this to the n-1 cube cross some fixed t. So so this is we should restrict it to an open neighborhood of this one. This is a one parametric family of sections, not holonomic yet, of sections in the jet bundle. Yes, where t varies in the interval. And now we can do now this has codimension in the big cube. Yes. So we're taking some slice. This has codimension. So we're taking a slice at some t. So it's this way, yeah, it's t. Now this has some codimension in the bigger cube, so we can do holonomic approximation of this one. That's done. So what does holonomic, and we can do holonomic approximation with one parameter. We can do it one parametrically. So what is happening is that for this t, we need to wiggle this embedding now. So we need to do this wiggling as Dani describes, and then we can take a little neighborhood of this one, and on that one we find a holonomic approximation of our section, and we can do that for every t. Yeah, so we have another t, we get another wiggling, right? Okay. All right. Now let's think about this wiggling. So so I'm going to do it relative to the boundary. I'm assuming near the boundary it's already holonomic. So I don't have to do anything near the boundary. Okay, so the wiggling is not at the boundary, it's starting somewhere here. So for some t, we need to do wiggling. Now for some nearby t, we also need to do wiggling. And if I'm careful, because there's this choice of really how we choose this, I can choose it carefully that for the next ones, they don't overlap. That I'm just, because as if you remember Dani's proof, there was really freedom to choose these functions nicely. Yeah. So I can choose it in such a way that all these wigglings for all possible t's never overlap, and they all together define me a diffeomorphism H, which is mapping these horizontal pieces onto the wiggled pieces. Okay, it's just okay. One really has to go back to the proof and say, okay, in the proof, I'm just choosing these functions carefully now, so that I get this picture. So this is some diffeomorphism. Okay, now over each of these guys, we have now some holonomic approximation ft. And we need to, so I can, if I think of that, this is some diffeomorphism, if I think of that in terms of this picture, which is easier, then it means I have holonomic approximations near each of these strips. But I need to go from one, I'll say, I'm actually working there, but I think it's just easier to think here, yeah? So I need to go from one of those to the other one, and I need to interpolate. And the way to interpolate will be to say I take another nearby one, and I can interpolate going from this one to this one, to this one to this one by doing this kind of multi-folded business. So I can and then I have a lot of space in this direction, and I move very little in this other direction, and then the same computation that Dani did allows us to do it here. Now I actually going to transport the picture over here, and I'm doing this interpolation here. So I'm not using this invariance of the differential relation. So I don't want to actually pull back anything and talk about here, but the way to do it is that I can take this pullback image. I take a multi-folded cube over this one. So this is the standard cube. But I view this as a multi-fold over here.
But certainly, don't you want to draw the cusps going vertically?
No, that's what I thought first, and I think we don't, because we're really following this one, and we want to vary t. We want to go from one t to the other, right. And I think the cusps go this way. We'll discuss it after, but I think the cusps want to go this way. Because you need to move in the vertical direction, and we want to do it so that we keep it we keep the jet place close. Okay, well, let's discuss it afterwards. So I think I claim that this somehow is the picture. Otherwise, I correct myself in the third lecture. Yeah, if Dani convinces me otherwise, then I'll change the picture. But I think this is a picture. And then this will be your multi. So you take this composition, and that is your multi-varied approximation.
Sorry,
Yes.
something. Can you explain again why we needed to go to the multi-cube?
Yes, because we have the
Like, why couldn't you interpolate on the right-hand side like you did on the left-hand side?
because this every ft is only defined on a neighborhood of these guys, and as you vary from, you need to. So they do not define one function here really. It's still a whole family of functions parameterized by t. Yeah. And I need to, out of it, I need to make it one map which is defined on some object and is a section in this jet bundle. And the way to do it is that I discretize in the t's and then interpolate between them. So,
Maybe a comment.
Mhm.
So I mean, because like I guess the way we wrote it instead, I mean, you could say instead of using this multi-fold to kind of emphasize this multi-valued idea, you could say, I just map from the cube directly into jet space, but I have to do it zigzagging over my original cube anyway. I mean, you could imagine I'm mapping IN to the jet space doing trrr, but when you project back to your original cube, I mean, kind of this multi-fold picture is showing up. So
Mhm.
you can formalize it in different ways, but
Yes,
this multi-valued thing has to appear somewhere.
yeah, right. Mhm. I'm actually going to switch to this other picture now. So this is some of the second steps. So once we get away from the multi-valued picture to one picture where we're turning back and forth. Yeah, and then we'll see the wrinkled picture. That's somehow what. So, okay, so you're okay with this one? Yeah.
Maybe one question about this. Where was it? These multi-valued holonomic sections? I'm not so familiar with non-Hausdorff spaces, but can you say something about?
No, I'm neither. So at first I was very much opposed to that. You can't do differential geometry on non-Hausdorff. I think it's important to keep in mind that, I mean, the only use of that is we want to be able to talk about smooth maps on this and their jets. We're not doing anything else. We're not introducing any other geometric objects on these spaces. And for that, it doesn't matter. We don't need it to be Hausdorff.
But even yeah, I just don't know anything about this, but derivatives on non-Hausdorff spaces?
Yeah, it doesn't matter. No, I mean, this has local charts, which are diffeomorphisms to open subsets in Rn, and you can talk about derivatives and overlaps. I mean, the transition functions are smooth diffeomorphisms and everything that is well defined. The whole local theory is well defined. You only run into trouble once you start to do any more global objects. You want to construct a remaining metric on that or whatever. You need a partition of unity, and I don't know. Then you might run into difficulty. But if you just do local theory, it's just a topological space. Forget Hausdorff. I'm so used to say like a topological Hausdorff is not Hausdorff. Yeah. It's a topological space, which has a covering by open sets, and on those open sets you have homomorphisms to open subsets of Rn, such as the transition functions are smooth, and that allows you to do all the local theory. Fine, okay. That's it. Yeah, and we're not doing anything else.
Just a bit confused about how you find the map out of this quotient. Like you had maps on these lines. On these slices of the cube, and then somehow you're building a map on this quotient space. So don't you want that FE and FE prime agreed on these intervals?
So the way to build the map is that you have a map defined here, and you have a map defined here, like on neighborhoods, actually on overlapping.
But these maps, like they don't talk to each other. Each one is separate, right? Like
Yeah. They're separate maps, but they are somehow defined on open neighborhoods, and those open neighborhoods overlap if you choose them very close to each other, and then you can interpolate by saying as you go. Okay, so how to say that? Yeah, you need to, as you glue this one to this one, you need to interpolate from this one to that one. So there's a short interpolation happening. You need to go from one to the other. Yeah, you cannot just say it's this one on this slide, this one on that slide, because they don't match up. You need to do some interpolation along the regions where along the paths where you connect. But you want to say you can do this interpolation slowly because you have enough space to move here, and you can interpolate slowly so that it remains close. So the whole jet remains close. Yeah. Okay.
And so where did you use that it was the fact that the perturbation was the identity near the boundary of the cube? Where did you, oh, you'll do this inductively, that was the thing.
Yes. Yeah, we do this inductively. So we already made it holonomic somewhere, and then we need to do the next cube, and yeah.
I'm very confused about the quantifier.
Yeah.
So we had the multi
Yeah.
fold is by no means like non-core.
No. So the quantifiers is given f. There exists. So first quantifier is here. There exists some multifold, and there exists a multi-section over that multifold, such that this is true. Yeah. So and both v hat and f hat depend on the given f. So depending on the f, I have to somehow choose this finer with more sheets, with more zigzags. Okay, so now we have 5 minutes. So. Now, the second ingredient we're going to need is so-called wrinkled right inverse of a multifold. It's not really a right inverse, but I don't know. Okay. So we have so the definition of this is the following, that it's, let me draw the multi here, v hat over v, and then it's call it W. So the claim is there exists, it's actually not a definition, it's definition and a lemma at the same time. So there exists a W, which is a wrinkled immersion or submersion, because here we are in the same dimension, such that it lifts to some W hat, which will then also be a wrinkled immersion. So that this diagram commutes, and such that if you take the regularized differential of this wrinkled immersion downstairs, it's homotopic to the identity. Meaning that the map itself from V to V is homotopic to the identity map, and also its differential over it is homotopic to the identity. Yeah, so with it's regularized differential because it's wrinkled. Yeah, and the proof is very easy. So that I can just explain. You do the one-dimensional case. So for the interval, I can draw you a picture. So here's the interval, 0 to 1. And now we're looking at this kind of, actually, this, but it doesn't. Yeah, so we do this in a function. And then this is a map from the interval. So this is the graph of W. It's going from the interval to the interval. And I claim that this is our W. And why? Because we're going back and forth. So this is the first interval here. Let's say the first interval is slightly larger than this one. But this is the part where this is glued to the second interval. On the second interval, we're turning back. So this we have this covering by the multifolded interval here. Yeah, so the first one is this one. Then there comes the second one, which is going down slightly below this one, which means that on the multifolded interval, we go forward on the first interval. Then we switch over to the other one because here they're glued. We go back on the second interval. We switch over to the third interval. We go forward on this one, and we go backwards. So this map W, in fact, lifts to a map to this multifolded interval. I mean, I can view it as a map from the interval to the interval, just this function, standard function. But I can also, out of it, I can make a map which goes from the interval to the multifolded interval, because just by switching branch at every turn. Okay. And then when you project back, of course, you get something which is just going from the interval to the interval and it's wiggling back and forth. And this is obviously homotopic to the identity. Yeah. Okay. So that's it. And then for the multifolded cube, because the multifolded cube is really just an n-1 cube times the multifolded interval and then doing some cutoff. So you just do this thing and you just need to cut this function off to the identity near the boundary. And you get it also there. Yeah. So then you get it for a multifolded cube, and a multifold is just something where everything happens on some embedded cube. So nothing, right? So then maybe should I stop? I think yeah. Or, if I have a couple of minutes, then I will finish the proof, because everything is set up so I can actually give the proof of the for the wrinkle submersion in the equidimensional case, because it's now just combining these two steps. Okay, so I don't have to repeat everything. So now the proof of the wrinkled submersion theorem for n equals q. So in the equidimensional case, and so what is the setup? We are having D to W, but now they're of the same dimension. We're given some map F, and it's covered by Python epimorphism. And we want to transform it into a wrinkled version. So the first thing is we can make it a multi-valued wrinkled map. So we get a multifold V hat, and we get F hat, a multi-valued submersion. We do multi-valued holonomic approximation. We can approximate it by a multi-valued submersion. But now we have a section of this one. We can go from here to there by our right inverse. So it's a wrinkled right inverse. And then we just, so I think this was called F0. Yeah. And then we just define F1 hat, or F1 just as I think I should maybe call this F1 hat, so it's a new one. F1 we do F1 hat composed with W. And that is now this. So this is now a wrinkled submersion or immersion in this case. And so this, why? Because this is a wrinkle. This is wrinkled, and this is an immersion, which is the same as a submersion in this dimension. And if you have a wrinkle and you compose, I mean, you post-compose it with an immersion, it's still wrinkled. So that's why I need the equal dimensions. So an immersion composed with a wrinkle is wrinkled. Now, a submersion composed with a wrinkle need not be a wrinkled submersion. So that's why I need the dimension condition here. In equal dimensions, submersion is the same as immersion, and I can post-compose a wrinkle with an immersion. It's still wrinkled, and then this is the proof. And then in the beginning of the third talk today, I will briefly comment on what one needs to do extra to deal with the other case. Now, thank you.